There's a ghost in the universe. It is the most profound and persistent phantom in all of existence. It does not haunt old houses or lonely corridors, but the vast, silent spaces between the stars. It is a presence that we cannot see, cannot touch, cannot feel, and yet it is there. It is the invisible scaffolding upon which our entire cosmos is built. It is the silent shepherd that guides the waltz of galaxies. Its gentle, unseen gravity is the reason you and I are here at all, and it makes up almost a quarter of everything that is. This is the story of that ghost, the story of dark matter. Hello there, and welcome back to the Drowsy Cosmos, our quiet little corner of reality where the deepest mysteries become a gentle, winding path towards sleep. Tonight, we are embarking on a quiet investigation, a gentle search for the unseen, the unknown, and the essential. We are looking for the ghost in the cosmic machine. And as we begin this search together, scattered all across the world in our own quiet spaces, I would love to know, what time is it for you right now as you join me on this journey? It feels fitting, doesn't it? To begin a story about an invisible presence by acknowledging our own unique, invisible place in the river of time. If you find this gentle exploration helps to quiet your mind and soothe your spirit, I would be so very grateful if you would give this video a like and perhaps subscribe. It helps this peaceful search party of ours reach other souls who might be looking for a calm and gentle mystery to unravel before they drift off to sleep. And as always, please feel no pressure to see this investigation through to its end. If my voice becomes a soft, steady hum and the ideas a comfortable pillow for your thoughts, then our mission is a success. So now, let the world outside your window fade away. Let your body grow heavy and still. And let's begin our search for the beautiful, silent ghost that holds our universe together. Our story begins, as many great detective stories do, with a single nagging clue, a small, persistent observation that just didn't make any sense. For most of the early 20th century, our picture of the universe was a bright and straightforward one. The cosmos was made of the things we could see: brilliant stars, glowing nebula, and the great, swirling cities of light we call galaxies. We believed that if we could just count up all the light from all the stars in a galaxy, we could calculate its total mass, and from that, we could understand its gravity. It was a neat, tidy, and logical picture. The universe was a well-lit room, and everything of importance was visible to us. But in the 1930s, a brilliant and famously cantankerous Swiss-American astronomer named Fritz Zwicky was studying a colossal structure called the Coma Cluster, a vast congregation of over 1,000 galaxies, all bound together by their mutual gravity. He was watching the way these galaxies moved, the way they danced and orbited around the cluster's center. He knew, based on the laws of gravity established by Newton and refined by Einstein, that for a cluster of this size to hold itself together, it must have an enormous amount of mass. The gravitational pull needed to be strong enough to prevent all those individual galaxies from simply flying off into the void. So he did the logical thing. He carefully estimated the mass of all the visible stars in all the galaxies of the Coma cluster. He added it all up, and then he calculated the total gravity that this visible matter should be producing. And this is where he found the clue that would haunt cosmology for the next century. The gravity he calculated was nowhere near enough, not even close. Based on the amount of visible matter, the galaxies in the Coma cluster should have been moving much, much more slowly. At the speeds he was observing, the cluster should have been flying apart. It should have disintegrated billions of years ago. For it to be as stable and cohesive as it was, there had to be an incredible amount of extra gravity holding it all together. Zwicky calculated that there must be hundreds of times more mass in the cluster than what he could see. He called this missing mass dunkle materie, or in English, dark matter. It was a radical, almost unbelievable claim. He was suggesting that the vast majority of the universe was simply invisible to us, that the well-lit room we thought we knew was in fact mostly dark. For decades, his idea was largely ignored. He was a man known for his difficult personality and his out-of-the-box ideas, and the scientific community was not yet ready for such a profound shift in perspective. The problem of the missing mass was treated as a curious anomaly, a puzzle that would likely be solved with more precise observations. Perhaps there was just a lot of faint, unseen dust, or dim, burned out stars that Zwicky hadn't accounted for. The universe, most astronomers still believed, was made of the familiar stuff of atoms. But the ghost would not stay quiet. Decades later, in the 1960s and 70s, another brilliant and meticulous astronomer, Vera Rubin, would find the same ghost haunting not just distant galaxy clusters, but individual galaxies, including our own next door neighbor, the Andromeda Galaxy. Vera Rubin was a pioneer in her field, a woman working in a male dominated world, and her work was defined by its precision and its patience. She was not looking at galaxy clusters, but at the graceful, spinning motion of single spiral galaxies. She was measuring how fast the stars on the outer edges of these galaxies were orbiting the galactic center. Again, the logic of gravity was simple and clear. Just like in our own solar system, where the inner planets like Mercury move very fast and the outer planets like Neptune move very slowly, the stars on the outer edges of a galaxy should be moving much more slowly than the stars near the bright, dense center. The vast majority of a galaxy's visible light, and therefore its visible mass, is concentrated in the central bulge. As you move further out, there are fewer stars, and so the gravitational pull should get weaker, and the orbital speeds should drop off significantly. But that is not what Vera Rubin found. With painstaking precision, she measured the speeds of stars at the very edges of galaxies, in their faint, dark, and seemingly empty outer regions. And she found that they were moving impossibly fast. They were orbiting at the same speed as stars, much closer to the center, and in some cases even faster. Imagine watching a spinning merry-go-round. The horses on the outside edge are moving much faster than the ones near the center. Now imagine a merry-go-round where the horses on the absolute outer edge were moving just as fast as the ones in the middle without being flung off. It would defy all logic. There would have to be some invisible structure, some unseen weight holding those outer horses in their circular path. This is exactly what Vera Rubin had discovered. The galaxy rotation curves, as they are called, were flat. They did not drop off as expected. The only way to explain this was if the galaxies were embedded in a vast, invisible, and spherical halo of some unknown substance, a halo of dark matter. This time, the evidence was too precise, too consistent, and too widespread to be ignored. From galaxy to galaxy, the same strange story was being told. The visible, shining part of a galaxy, the part that we see and admire in beautiful photographs, is just the tip of the iceberg. It is like a small, luminous jewel embedded in a much larger, much more massive, and completely invisible crystal ball. The ghost that Fritz Zwicky had glimpsed in the coma cluster was not an anomaly. It was everywhere. The universe was not a well-lit room. It was a vast, dark cathedral, and the stars and galaxies were just the faint, scattered candlelight, giving us our only hint of the immense, unseen architecture that surrounded us. So what is this ghost? What is this dark matter that seems to make up the vast majority of the mass in our universe? The honest answer, the one that is both humbling and thrilling, is that we do not know. But science is a detective story, and when you can't see the culprit, you start by building a profile. You deduce what it must be like based on the evidence it leaves behind. And over the last few decades, we have built a remarkably detailed profile of our cosmic ghost. First, we know what it is not. It is not just dim, normal matter that we have failed to see. It is not vast clouds of dust or swarms of black holes or countless dead stars. We have looked. Our models of the early universe, which so accurately predict the amount of hydrogen and helium that should exist, place very strict limits on how much normal atom-based matter can exist in total. And that amount is only a small fraction of what's needed to explain the gravity we observe. The ghost is not made of the same stuff as you or me or the stars. It is something else entirely. It is something new. Second, we know that it is dark, and this means more than just that it doesn't shine. It means it does not interact with light in any way. It doesn't emit light, it doesn't absorb light, it doesn't reflect light. It is completely, utterly transparent. If you were holding a solid ball of pure dark matter in your hand, it would be perfectly invisible. Your hand would pass right through it. It is a substance that seems to exist in a kind of parallel reality, interacting with our world through only one single subtle force, the gentle pull of gravity. Third, we know that it is cold. In cosmology, cold doesn't just mean a low temperature. It means that the particles of dark matter are moving relatively slowly. This is a crucial clue. Because it is slow moving, dark matter is clumpy. It was able to gather together under its own gravity in the early universe, forming the great vast halos that would act as the cosmic nurseries for galaxies. If dark matter had been hot, meaning its particles were moving at or near the speed of light, it would have been too energetic to clump together. It would have just smoothed itself out across the cosmos, and the beautiful, intricate web of galaxies we see today would have never been able to form. The universe would be a much more uniform and boring place. So, our profile of the ghost is this: it is an unknown, invisible substance, not made of atoms, that does not interact with light, and whose slow moving particles have patiently sculpted the entire large scale structure of the cosmos through the gentle, persistent, and singular force of its own gravity. So, our cosmic detective story has led us to this point. We have a phantom on our hands, a substance of immense consequence, yet one that is utterly invisible to our most powerful telescopes. It is a ghost that leaves behind only one single subtle clue: the gentle, persistent, and undeniable pull of its own gravity. This presents a profound challenge. How do you map a landscape that you cannot see? How do you weigh a substance that you cannot touch? How do you track a ghost? For decades, the evidence for dark matter, compelling as it was, remained indirect. It was a necessary ingredient in our equations, a ghost required by the math to make the universe behave the way it does. But astronomers are observers. They longed for a way to not just deduce the presence of dark matter, but to somehow, in some way, see its effects directly. And the key to doing this would come, once again, from the profound and beautiful mind of Albert Einstein. In his theory of general relativity, he didn't just teach us that gravity is the curvature of space time. He also revealed a stunning consequence of this fact: that gravity can bend the path of light. Imagine space-time as a vast, flat sheet of glass. A ray of light traveling through it would move in a perfectly straight line. Now imagine placing a heavy weight on that glass. The glass will bend and warp around the weight. A ray of light passing near that weight will now follow the curve in the glass. Its path will be bent. This is what happens in the cosmos. Any massive object, a star, a galaxy, or a colossal cluster of galaxies, warps the space-time around it, and the light from any object located far behind it must travel through this warped spacetime to reach us. Its path is bent, just like light passing through a glass lens. This phenomenon is called gravitational lensing. At first, it was just a theoretical prediction, another strange and wonderful idea from Einstein's theory. But it was confirmed during a solar eclipse in 1919, when astronomers observed that the light from distant stars was indeed being bent as it passed by the immense gravity of our sun. It was a triumphant moment for science. But for our story, the most powerful application of this idea comes when we look at the largest structures in the universe. Imagine a colossal galaxy cluster, like the Coma cluster that Fritz Zwicky first studied. This cluster is an immense concentration of mass, and therefore it creates a huge and powerful gravitational lens in the fabric of spacetime. Now, imagine a single, very distant galaxy located billions of light years behind this cluster from our point of view on Earth. As the light from that distant galaxy travels toward us, it passes through the warped spacetime of the foreground cluster. The cluster's gravity acts like a giant, imperfect, cosmic magnifying glass. And what we see when we point our telescopes at such a cluster is truly magical. The light from the distant background galaxy is warped and distorted. We don't see it as a normal single galaxy. Instead, we might see its image stretched into a long, thin, beautiful arc of light, or we might see its image smeared and magnified. In some cases of perfect alignment, we can even see multiple images of the very same galaxy, its light having taken several different paths around the lensing cluster to reach our telescopes. These beautiful, ghostly arcs and multiple images are called Einstein rings, or gravitational arcs, and they are the universe's own way of allowing us to see the invisible. Because here is the crucial part of the story. When astronomers began to carefully measure these gravitational lenses, they found the same old problem that had haunted Zwicky and Rubin. The amount of distortion, the degree to which the light was being bent, was far, far greater than could be explained by the visible matter in the galaxy cluster alone. The stars and the gas in the cluster simply did not have enough mass, not enough gravity, to create the powerful lensing effects they were observing. Once again, the ghost was making its presence known. But this time, it was different. This time, we could use the distorted light from the background galaxies as a tool. We could use it to create a map. By measuring the precise shape and location of all those ghostly arcs and distorted images, astronomers could work backwards. They could calculate exactly how much mass must be present in the cluster, and, more importantly, where that mass must be located in order to produce the lensing effects they were seeing. And when they did this, they created the first true maps of the invisible. The results were breathtaking. The maps showed that the visible galaxies of the cluster were just small, bright islands floating in a vast, deep, and completely invisible ocean of mass. The gravitational lensing was being caused not primarily by the galaxies themselves, but by a vast, smooth, and enormous halo of dark matter in which the entire cluster was embedded. We could finally see the ghost's shadow. We were no longer just inferring its presence from the motion of stars. We were now mapping its distribution across the cosmos by watching the way its immense gravity bends the light from the most distant corners of the universe. It was as if we had developed a new sense, a way to perceive the universe not through light, but through the silent, invisible language of gravity itself. One of the most powerful and famous examples of this is a structure known as the bullet cluster. This is not a single galaxy cluster, but two entire clusters of galaxies that have collided with each other at incredible speed and have passed right through one another. It is a cosmic traffic accident on the grandest possible scale. When these two clusters collided, something interesting happened to their different components. The normal matter in the clusters, which is mostly vast clouds of hot gas, crashed into itself. Like two great waves of water meeting, the gas clouds slammed together, creating a spectacular shockwave of superheated plasma that we can see with our X ray telescopes. This hot gas, containing most of the normal visible mass of the clusters, was slowed down dramatically by the collision and was left lagging in the middle. But what happened to the dark matter? Because dark matter does not interact with itself or with normal matter except through gravity, the vast halos of dark matter from the two clusters did not crash into each other. They behaved like ghosts. They passed right through each other, completely unimpeded, and continued on their way, leaving the hot gas behind. Using gravitational lensing, astronomers were able to map the location of the mass in the bullet cluster. And what they found was a perfect smoking gun proof of the existence of dark matter. The map showed that the vast majority of the mass was not located in the center with the hot, glowing gas where all the normal matter was. Instead, the mass was located in two great invisible clumps on either side of the center, exactly where the halos of dark matter should be after having passed through each other like phantoms. The visible matter and the dark matter had been physically separated by the collision. We could see the normal matter in one place, and we could see the gravitational effects of the dark matter in a completely different place. The ghost had finally been caught in the act. This technique of gravitational lensing has now become one of our most powerful tools in cosmology. We use it to create ever more detailed maps of the invisible universe, to trace the intricate web like filaments of dark matter that connect the great galaxy clusters, and to understand the deep, hidden architecture that governs the cosmos. These maps reveal a universe that is profoundly beautiful and surprisingly organized. They show that on the largest scales, galaxies are not scattered randomly through space. They are arranged in a vast, interconnected structure known as the cosmic web. This web consists of long, thin filaments and dense, knot like clusters, all surrounding vast, empty regions called cosmic voids. And the invisible threads of this great web, the scaffolding upon which it is all built, are made of dark matter. The dark matter formed this structure first. In the early universe, its slow moving particles began to clump together under their own gravity, forming a vast, intricate network of halos and filaments. The normal matter, the stuff of atoms, was then drawn by gravity into these pre existing dark matter structures. The dark matter was the silent shepherd, patiently gathering the cosmic flock. The galaxies, stars, and planets we see today are just the luminous decorations, the bright lights strung along a much larger, much older, and completely invisible cosmic Christmas tree. And so the evidence has led us here, to a universe built upon a grand, invisible architecture, a cosmic web of dark matter whose patient gravitational influence has sculpted the entire visible cosmos into the beautiful, intricate tapestry we observe today. We have learned to map its shadow using the bent light of distant galaxies. We have seen its ghostly presence separated from normal matter in the aftermath of cosmic collisions. The case for its existence is, at this point, overwhelmingly strong. But for a physicist, this is not the end of the story. It is only the beginning of a new, even deeper mystery. It is one thing to know that the ghost is real. It is another thing entirely to know what the ghost is. Mapping the effects of dark matter on a galactic scale is a magnificent achievement, but it doesn't tell us about its fundamental nature. What is this mysterious, invisible substance actually made of? Is it composed of a new type of fundamental particle, something completely unknown to our current theories of physics? Can we ever hope to detect it directly? Can we ever hope to hold a piece of the ghost in our hands? This is the great challenge that has consumed a generation of particle physicists. It has driven them to build some of the most extraordinary and sensitive experiments ever conceived by humankind. It is a search that takes place not by looking up at the heavens with giant telescopes, but by looking down, deep into the earth, in the quietest, most isolated laboratories in the world. This is the hunt for a direct detection, a single, solitary, and unambiguous sign that a particle of dark matter has interacted with a particle of our own familiar normal matter. The challenge, of course, is immense. We are trying to detect a substance whose defining characteristic is that it barely interacts with anything at all. The ghost, by its very nature, does not want to be found. We know that we are, at this very moment, flying through a vast spherical halo of dark matter that surrounds our Milky Way galaxy. Our entire solar system is moving through a constant, invisible wind of these dark matter particles. Scientists estimate that hundreds of thousands of them are passing through your body, through this room, through the entire planet, every single second, and yet you feel nothing. They feel nothing. They pass through the dense matter of the earth as if it were empty space. They are phantoms in every sense of the word. However, some theories predict that very, very rarely, perhaps only once a year or once a decade in a vast vat of material, a single dark matter particle might just happen to collide directly with the nucleus of an atom of normal matter. It would not be a dramatic collision. It would be more like a faint, ghostly nudge. The dark matter particle would strike the atomic nucleus and transfer a tiny, tiny amount of kinetic energy to it, causing the nucleus to recoil, almost imperceptibly. The dark matter particle itself would then continue on its way, completely unaffected. The entire goal of these deep underground experiments is to try and detect that single, tiny atomic recoil. It is a search for the faintest possible whisper in a world that is filled with constant, shouting noise. The reason these experiments are built so deep underground, often in old mines or beneath mountains, is to shield them from this noise. The surface of the Earth is constantly being bombarded by a rain of high energy particles from space called cosmic rays. This cosmic radiation would create a constant storm of false signals, completely overwhelming the faint whisper of a potential dark matter interaction. But miles of solid rock act as a natural protective barrier, filtering out almost all of this cosmic noise and creating an environment of profound and almost perfect silence. In these deep, quiet laboratories, scientists have built detectors of incredible sensitivity. One type of experiment uses large tanks filled with a super pure liquefied noble gas like xenon or argon. The liquid is kept incredibly cold and it is surrounded by a battery of highly sensitive light detectors called photomultiplier tubes. The idea is simple and beautiful. If a dark matter particle happens to pass through the tank and strike the nucleus of a xenon atom, the recoiling nucleus would disturb the surrounding atoms, causing them to emit a tiny, fleeting flash of scintillation light. At the same time, the collision would knock a few electrons loose, which would then be guided by an electric field to the top of the detector, creating a second, slightly delayed signal. By looking for this unique two-part signature, a tiny flash of light followed by a tiny puff of charge, scientists can distinguish a potential dark matter event from the background noise of normal radioactivity. Other experiments use a different approach. They use crystals of a material like germanium, cooled to temperatures just a fraction of a degree above absolute zero, the coldest possible temperature in the universe. At these extreme temperatures, the atoms in the crystal are almost perfectly still. If a dark matter particle were to strike one of these atoms, the tiny recoil energy would be deposited into the crystal as a minute vibration, a tiny pulse of heat. This faint rise in temperature, this phonon signal, is then measured by incredibly sensitive thermometers. For decades, these experiments and others like them have been running in the deep, silent darkness, listening patiently. They have become more and more sensitive, using larger and larger detectors, filtering out more and more background noise. They are pushing the very limits of our technological ability to measure the small and the faint. And so far, they have found nothing. A profound and telling silence. But this silence is not a failure. In science, a null result, a non detection, is also a form of data. With every new experiment that runs and finds nothing, we are able to rule out certain possibilities. We are able to say that if dark matter is a certain type of particle with a certain mass and a certain interaction strength, then we should have seen it. And since we haven't, it must be something else. We are narrowing the search. We are learning more about the ghost by mapping the places where it does not hide. This persistent silence from our direct detection experiments has led physicists to consider a whole range of fascinating possibilities for what dark matter could be. The leading candidate for a long time has been a type of hypothetical particle known as a WIMP. WIMP stands for Weakly Interacting Massive Particle, and the name is a perfect description. Massive means that these particles would be quite heavy, perhaps 100 times more massive than a proton. This would explain why dark matter has such a strong gravitational effect. Weakly interacting means that they would interact with other particles through the weak nuclear force, one of the four fundamental forces of nature, in addition to gravity. The WIMP hypothesis was so popular for so long because of something that physicists call the WIMP miracle. It turns out that if you calculate how many of these particles should have been created in the hot, dense soup of the early universe, and how many should have survived until the present day, you get an amount that matches the observed amount of dark matter almost perfectly. It seemed too good to be a coincidence. It felt like the universe was giving us a very strong hint. Our direct detection experiments were designed primarily to look for WIMPs. But their persistent silence has led many physicists to start looking elsewhere, to consider possibilities that are even more exotic, even more ghostly. Perhaps dark matter is not a WIMP. Perhaps it is a particle called the axion. Axions are also hypothetical, but they come from a different area of theoretical physics, proposed to solve a different problem entirely. Unlike the heavy WIMP, the axion would be incredibly light, billions or even trillions of times less massive than an electron. There would be a vast cosmic sea of them, a dense cloud of countless axions that collectively make up the dark matter halo. And because they are so light, they would not cause an atom to recoil in our detectors. Instead, theory predicts that in the presence of a very strong magnetic field, an axion could very rarely transform into a photon of light, a tiny, faint flash of microwaves. And so, a whole new generation of experiments are now being built to look for this signal. They are, in essence, trying to build a dark matter radio, tuning their detectors to try and hear the faint, static like hiss of axions converting into light. And so the search continues, branching out into new and exciting directions. The silence from the WIMP experiments has not led to despair, but to a flowering of creativity. The ghost, it seems, is more subtle, more elusive, and perhaps far more strange than we initially imagined. The idea of the axion, this incredibly lightweight and abundant particle, has opened up a whole new frontier in our hunt for the invisible. But the possibilities do not end there. As we have peered deeper into the cosmos and as our simulations of galaxy formation have become more and more sophisticated, a few small but persistent discrepancies have emerged. Our standard model of dark matter, the simple, cold, non interacting model, is incredibly successful on the largest of scales. It perfectly explains the structure of the cosmic web and the rotation of giant galaxies. But on smaller, more local scales, things are not quite so perfect. For example, our simulations predict that the center of a galaxy's dark matter halo should be very dense and cuspy, with the density rising sharply toward the very middle. However, when we observe actual galaxies, especially smaller dwarf galaxies, we often find that their dark matter cores are much less dense, more cored, and spread out. Our simulations also predict that a large galaxy like our own Milky Way should be surrounded by thousands of smaller satellite dwarf galaxies, trapped in its gravitational pull. Yet we have only found a few dozen. Where are all the missing satellites? These are not cracks in the foundation of the theory, but they are nagging little details, small pieces of the puzzle that don't quite fit. And they have led some physicists to wonder if our profile of the ghost is missing a key detail. Perhaps dark matter is not completely non interacting after all. This leads to the fascinating idea of self interacting dark matter, or SIDM. In this model, dark matter particles do not interact with our normal matter, but they can, very rarely, interact with each other. Imagine the particles of the dark matter halo not as a completely collisionless cloud of ghosts, but more like the molecules of a gas, which can occasionally bump into and bounce off one another. This small change, this addition of a tiny amount of self interaction, could have profound consequences. Over billions of years, these gentle internal collisions within a dark matter halo would tend to smooth things out. They would transfer energy from the dense inner regions to the sparser outer regions, effectively flattening out the central cusp and creating the softer core that we observe in many galaxies. It could also explain the missing satellites, as this self interaction might make it harder for the smallest dark matter halos to form and hold on to their galaxies in the first place. The idea is a beautiful one. It suggests that the dark matter sector of our universe might have its own rich and complex physics, its own set of forces, its own dark chemistry that we are only just beginning to imagine. It would mean that the ghost is not a solitary phantom, but a member of a vast, invisible society with its own rules of engagement. And the theories become even more imaginative. Perhaps dark matter is not just one particle, but a family of them, a dark sector as rich and complex as our own standard model of particles. Perhaps there is a dark photon that carries a dark light, allowing dark matter particles to communicate in a way we can never see. Perhaps dark matter feels a dark weak force or even a dark strong force, creating complex structures on scales we cannot yet probe. The universe, in this view, would be a place of two parallel realities, interwoven but almost completely separate. Our world of light and atoms, and a shadow world of darkness and unknown particles, each living out its cosmic story, touching only through the gentle, universal, and inescapable embrace of gravity. And yet, through all of this exploration, through all of this creative and brilliant theorizing, a small, persistent, and radical question has always lingered in the background. A question that challenges the very foundation of our search. What if we have been chasing a phantom that isn't there at all? What if the problem is not a missing substance? What if the problem is that our understanding of gravity itself is incomplete? This is, in many ways, the most audacious and challenging idea of all. It suggests that the ghost is not a particle to be found, but a flaw in our own theories. For over a century, Einstein's theory of general relativity has been our bedrock, a theory of gravity that has passed every single test we have thrown at it with flying colors. But perhaps on the very largest of scales, the scales of galaxies and galaxy clusters, it begins to break down. Perhaps there is a new, deeper theory of gravity waiting to be discovered. This line of thinking has led to a class of theories known as modified Newtonian dynamics, or MOND. First proposed in the 1980s by the Israeli physicist Mordechai Milgrom, MOND offers a simple and, at first glance, incredibly elegant solution to the mystery of the flat galaxy rotation curves. MOND suggests that Newton's law of gravity, as we know it, is perfectly correct in places where gravity is strong, like here in our own solar system. But in regions where gravity becomes incredibly, incredibly weak, like on the far outer edges of a galaxy, the law itself changes. Specifically, the theory proposes that in these low acceleration environments, the force of gravity fades away with distance much more slowly than we expect. This would mean that the stars on the outer edges of a galaxy feel a stronger gravitational pull from the center than our current theories predict. And this stronger pull would be exactly what is needed to explain why they are moving so fast. With this one simple modification to the law of gravity, the need for dark matter to explain galaxy rotation curves simply vanishes. There is no missing mass. The stars are moving fast because gravity itself is stronger out there than we thought. For many years, MOND was seen as a fringe idea, a clever but ultimately flawed alternative. One of its biggest challenges was explaining the observations of galaxy clusters, like the Bullet Cluster. How could a simple change to the law of gravity explain how the visible matter and the gravitational mass could be in two different places? But proponents of MOND have continued to develop and refine their theories. More complex, relativistic versions of MOND have been proposed, which attempt to account for these more challenging observations. They argue that while their theories may not yet be perfect, they have had some remarkable successes. MUND, for example, not only explains that galaxy rotation curves should be flat, it actually predicts the exact shape of those curves with incredible accuracy, often better than our standard dark matter models. And so, the great cosmic debate continues. On one side, we have the vast majority of physicists and astronomers who believe that dark matter is a real physical substance, a new particle that is waiting to be discovered by our ever more sensitive experiments. The evidence from gravitational lensing and the structure of the cosmic web is for them too powerful to ignore. And on the other side, we have a small but persistent group of researchers who believe that we are on the verge of a new revolution in our understanding of gravity itself. That the ghost in the machine is not a new component of the universe, but a ghost in our own equations. It is a beautiful and humbling place to be in the history of science. We are faced with a profound mystery and two equally profound possible solutions. Either 85% of the matter in our universe is made of a completely new, unknown substance that we have never detected, or our most fundamental theory of gravity, a theory that has stood for a century, is in need of a major revision. Both possibilities are staggering. Both possibilities would change our understanding of the cosmos forever. And so, we find ourselves standing at a great crossroads in our understanding of the cosmos. Down one path lies a universe filled with a new and exotic form of matter, a ghostly particle that has silently shaped our world from the very beginning. Down the other path lies a new understanding of gravity, a revision of the very laws that govern the dance of stars and galaxies. Both paths lead to a universe that is richer, stranger, and more wonderful than we had previously imagined. And perhaps in this quiet moment before sleep, it doesn't matter which path turns out to be the correct one. Perhaps the true beauty of this story lies not in the final answer, but in the search itself. The story of dark matter is a perfect illustration of the scientific process at its most humble and its most grand. It is a story that begins with a single nagging observation that doesn't fit our expectations. It is a story of patient, meticulous work, of brilliant minds like Fritz Zwicky and Vera Rubin, who dared to believe the evidence of their own eyes, even when it contradicted the comfortable consensus of their time. It is a story of incredible creativity and ingenuity, of physicists building detectors in the deepest, quietest places on Earth, listening for a whisper that may or may not be there. It is a story of theorists, dreaming up new particles and new forces, or daring to question the foundations of our most cherished theories. And above all, it is a story of profound humility. It is a reminder that what we can see, what is accessible to our senses and our instruments, is not the full picture. The universe we perceive, the bright and beautiful world of starlight and galaxies, is just one layer of a much deeper, much more complex reality. It is a reminder that the cosmos is under no obligation to be simple or to conform to our common sense expectations. The ghost in the machine, whether it is a particle or a new law of physics, teaches us a valuable lesson. It teaches us that the universe is filled with things that are quiet, subtle, and unseen, but which are nevertheless essential. It reminds us that the most powerful forces are often the most gentle, the most patient, and the most silent. The dark matter, if it is real, has been sitting here, surrounding us, passing through us for 13.8 billion years. It has never rushed. It has never made a loud noise. It has simply, through its gentle, persistent, and unwavering gravitational presence, sculpted the entire large scale structure of the universe. It built the cosmic web. It gathered the gas that would form the first stars. It created the great stable halos in which galaxies like our own could be born and thrive. It is the silent, invisible, and foundational architect of our cosmic home. Without its patient, quiet work, the universe would be a barren and unstructured place. The very atoms that make up your body would likely never have found a home in a star or a planet. The ghost is not a frightening phantom. It is our silent, creative ancestor. And if it is a new law of gravity that awaits us, the lesson is just as profound. It would mean that even our most successful and celebrated theories are just approximations, just steps on a much longer journey toward understanding. It would remind us that we should always be ready to let go of our old ideas, no matter how beautiful or successful, when the universe presents us with new and compelling evidence. It would be a testament to the endless frontier of knowledge, a promise that there are always deeper, more elegant, and more beautiful truths waiting to be discovered. And so, as we bring our gentle investigation to a close, let us not worry about the final answer. Let us instead simply rest in the beauty of the mystery itself. Let us bring our awareness back one last time from the cosmic web, from the deep underground labs, from the very nature of gravity itself. Let us bring our focus all the way back to this room, to this bed, to this quiet and peaceful moment. Feel the gentle but persistent force of gravity holding you comfortably in your bed. It is a familiar, comforting presence, and yet we now know that this simple feeling is connected to the grandest mystery in all of cosmology. The very force that keeps you grounded is the same force that reveals the presence of the great cosmic ghost. You are, in this moment, participating in the same cosmic dance that revealed the mystery in the first place. As you lie here, in the quiet and the dark, you are in a perfect state to appreciate the nature of this mystery. The world of light and sound and busyness has faded away, and in its place there is a quiet, unseen presence. The presence of your own consciousness, your own thoughts, your own dreams. Like dark matter, your inner world is invisible to others, but it is the scaffolding upon which your entire experience is built. So let the ghost of the universe be a gentle companion as you drift off to sleep. Let it be a symbol of all the quiet, unseen, and supportive forces in your own life. Let it be a reminder that you are part of a story that is far grander, far more mysterious, and far more beautiful than you can ever fully know. There is nothing left to figure out tonight. The cosmic detectives can rest. The search can be paused. All that is left is to surrender to the gentle, unseen gravity of sleep. Allow it to pull you down into a state of deep and restorative peace. Let your thoughts become like the phantom particles passing through your mind without interacting, without disturbing your growing stillness. Thank you for joining me on this journey into the heart of the cosmic darkness. I hope it has filled you with a sense of wonder and a profound and lasting sense of peace. If you have found a moment of calm here in our quiet corner of the cosmos, a like or a subscription is always so deeply appreciated. It helps our small, drowsy universe to continue its gentle search for knowledge and for rest. But for now, the search is over. The mystery can wait. All that matters is this moment, the darkness, the quiet, and the gentle, invisible presence that is guiding you as it guides the galaxies toward a state of perfect, peaceful, and well-deserved rest. Sleep well. Dream of the invisible. The silent ghost of the universe is watching over you.